Hello everyone, welcome back. Today I have a very special video. I have noticed while giving several, while making tutorials and explanations, guides and wikis, I have noticed that it's still difficult for newcomers sometimes to understand uh, the leap between the occidental syntax and what is actually the CPU, the UXN doing. So today I developed a paper computer. Uh, Let me show you one of the existing ones. So we can see in Wikipedia there is this very famous WDR paper computer. And here it says, let me see. It was created in the 1980s when computer access was not yet widespread in Germany to allow people to familiarize themselves with basic computer operation and assembly line programming languages. Uh, so in this same spirit, as you can see here in this image, it is very simple. You only have a few instructions. So this would be your RAM, and then you only have two registers. But with this, they were able to showcase how a computer worked. There are other examples. Let me just check here. There is the GENIAC, the Cardboard Illustrative Aid to Computation, as well as the Little Man computer. This one is not a paper computer, it's actually a mechanical digital computer kit. This was the second version. And the Turing Tumble is also a physical device. So let me also show you here the GENIAC is also a mechanical computer, okay? So the one I'm looking is this one. Cardboard Illustrative Aid to Computation. Of course, there are also emulators for these paper computers. But as you can see here, this one, let me make it bigger. This one actually had a sort of cardboard where you could push and pull these slides so that it told you, for example, the value here in the register. I think this is very cool design as well. Let me go back. This is a very cool design as well, and this one has a little bit more instructions, as you can see here. But it is still very minimal. Okay, so now there's also the Little Man computer. The Little Man computer also has virtual emulators, but as you can see, this is a machine that is small enough that you can do all the computations by hand in order to learn how assembly and CPUs work. So one thing I like about this version, here we can see some examples. The syntax, let me see. There is actually a game called I forgot the name. Let me see. It is a sack like for Android. It is the human resource machine. So this game is actually based on this one, on the Little Man computer. However, in this case, it is gamified, and the little man in the computer is this guy that you play with. It has a very nice UI, which is actually very usable when you are using your thumbs on the Android. Although this is also for PC on Steam, I believe. And also there is the little stack computer. Little man stack computer. Yes, here it is. So this is a variation of the little man computer, but this mixes a stack machine and register machine. Okay, here is the architecture, how it looks like. And then we can see, for example, some assembly. No, where it is? Emulator. So it has an emulator. We can go here, LMSM emulator. And you can see this is the RAM, the assembly. Here you would write high-level code in a language called Perl. And then you can see here the console output. So inspired by this design and all the previous ones as well, I have developed a paper computer for UXN. I have made several tries before, but I think this time is a good resource, not only for experimenting, but for actually learning how a real UXN, well, a real virtual UXN CPU works. So the only difference between this computer and the real thing is that this one has much less RAM. So by default, UXN has 64 kilobytes of RAM. We can see here in the Barbara specification. No, wait, it was here. I don't find it. Give me a moment. Oh, then it is here in UXN. No. Okay. Maybe it was moved somewhere else. Stack pointer. Yeah, I don't know where it went. Because it showed like the memory layout. Um, okay. Okay, and no problems. Either way, I'm going to edit this video once I have finished the stream. Well, probably tomorrow, not today, to make it a little bit more cohesive without all this sidestepping that always happens when we are doing live coding. Yeah, but I remember there was a table here. Well, anyways, oh, here it is. So it is under occidental memory, and this is all the memory the virtual machine has. So by default, you have 64 kilobytes for main RAM. That is 256 pages of RAM. Each page is 256 256 bytes. For example, here we have the 0 page, which is 256 bytes. A full UXN virtual machine would have 256 pages, totaling the 64 kilobytes. Then some emulators may have an expansion which allow you to have more memory banks, and you can go up to 1 megabyte if you add 16 more banks of 64 kilobytes each. Okay, so that is like the one side of the scale, but on this side we are going to do the complete opposite. Also, normally the stacks have a page for themselves, both the working stack and the return stack, and each one has 1 byte for their pointer. And for the devices, there is another full page just for the devices, and it is not shown here, but there is also one register for the PC, for the program counter, and this one is 16-bit wide. Okay, so let me now show you mxn. mxn is a development by D6, and this is basically a specification for smaller UXN machines. So it is a minimal UXN for limited systems. And you can see here that it has a specification for what is a mxn ABC. In this case, this paper computer is a mxn-200. Why is that? Because it has, this is the formula, we can run it here real quick. So for example, this says 2 to the A times 256. So that would be 2 times 2, then multiplied by 256. That gives us 1024 bytes, which is 1 kilobyte. Okay, then we have for B, that this is the depth of the size of the stacks. So in our case, the second digit is 0. So the formula here would be 2 to the 0 times 16. It gives us 16 bytes for each stack. And then we have another 0 for, which means there is no screen. Okay, and if we go here to the paper computer, we can see that the stacks have 16 bytes each, and then we have 4 pages of 256 bytes, totaling 1 kilobyte. Okay, I will go in more detail over this. Just let me finish the explanation. Okay, so this is what mxn is, and this is the normal memory layout. I have also explained what is a paper computer. Now I want to go here to the Occidental website. All these links, by the way, are in the paper computer, and the paper computer PDF is linked in the description of this video. Okay, so you can just follow these links to go to the pages I'm currently looking at. So here in the Occidental page, we have this little emulator, which we can run, and we can even select several examples. We can also go here to the paper computer and select this link here. Okay, give me a moment. I didn't copy. What is going on? Copy. There we go. And here is like a full page version of of this same widget without the tutorial. Let's go back to the tutorial real quick so I can just explain you. Here is the introduction. You can read all this in more detail, but I want to give my explanation today myself. However, we will be using some of these tables. Okay? So first, let's run this example that we have here, and we can see that this is a hello world. It just prints hello world to the console, and we can even restart it and step through. Okay, so we can see that the first opcode is a lit2, which pushes 2 bytes to the stack, which are these ones. And these 2 bytes are the address of the text label. So this is what is happening here. Then we enter this other section, and the first instruction we execute is a load absolute keep. This is loading the byte at this address, which is 48 in hexadecimal. If we go to the paper computer again, we can see I added here a link so you can go to an ASCII table, and here in the hex column we can check for the byte 48. Byte 48 is decimal 72, and it stands for the letter H in ASCII. Okay, so once we load this H here, we check, we duplicate it, so now we have it here duplicated, and then we are checking here if this is 0. If it is not 0, we will jump to this other label. This is an anonymous label, so it is the same as these ones. It is just that it doesn't have a name. So we could have done this as well, for example. Non-zero, and here instead of having this we could put another label, and this would have exactly the same outcome. Okay, that is all the anonymous label was doing. So we check if this is non-zero, we jump to this label here, and since 48 is non-zero, we are right now going to evaluate this. Oh, I'm sorry, I changed it. Non-zero like this. Yes. So let me go back to here. We are in the dupe. Then we check. Okay, now we are in this part. Here we pushed 1/8 to the stack. And after this, we are going to print this character by sending it to the device port 1/8. And as you can see here, we have an H. After we have this H, we increment the address that is still on the stack, and then we loop back. Okay, we repeat this until we reach this 0 null terminator byte. Let me go there. So if I keep stepping, you can see that the following letters are printed as well. We are in hello world. Okay, so right now we have on the stack the address of the exclamation mark. Now we have incremented this address, and we are now at the address of the null byte. Once we jump from here to here, we will load again the value, but this time it will be 0. So now we duplicate it and we test this again. If it is 0, this time it is indeed 0, so we need to clean the stack because we are done. We have 3 bytes left in the stack, the 0 we just loaded, and the address of the string. So now we are going to pop 1 byte, and then we are going to pop the remaining 2 bytes. And with this, the evaluation has concluded. Okay, I have made another video about a year ago explaining this same algorithm with the same interface. But today I wanted to go beyond this and dispel any magic that you may think it's happening. It is actually very simple. So simple that we can do it by hand without an external assembler. We will assemble the source code and we will evaluate it as well. Okay, so what we can do now is I will just copy this text. I have already copied it here in my document. So this is like a blank page, but here I have some examples. So if we go here to hello world, I have the exact same code in this part, but now let me make it a little bigger. You can see this just as reference. This is how it looks empty, and this is how it looks with the code loaded, with the bytecode. Okay, so how can we get this bytecode? We could click here where it says hex, and it would show us this code that you can copy. You can copy and paste it here. Well, if you are doing it like me on the computer, or if you are doing it by hand, you just write down these hexadecimal digits. I recommend using a light pencil so that you are able to erase and recycle the sheet of paper. Okay, so that is with this option we have here. We can also click the ROM button, and it will actually save the ROM file to disk. So now, for example, if I go to descargas, which is downloads for me, and we now should have saved.rom, and there it is. Okay, so that means that now I can run oxenqui save, and as you can see, it works here in my computer as well. Okay, let me do it again. This percentage sign we see here is because there was no new line at the end. We could add it, but this is all it means here, that it printed hello world without a new line, and then the program finished. Now I have here a program called oxendump that can allow us to visualize how this what these bytes mean. So I put save.rom like this, and now we have a dump of the hexadecimal code. However, notice here in the right we also have a view of the ASCII characters, if any. All the ASCII are in green. Any byte that is not a visible ASCII character is in another color. Okay, and if we check the hexadecimal code that it gave us here, we can see that it is the same code. The only difference here is that I have it colored and commented, okay? And it is 31 bytes in length. Okay, now that we have this, we can load the code directly into RAM, which is what I have done here, okay? I have another example here that I have not assembled because we are going to do it by hand ourselves. We are going to be both the assembler and the CPU in this case. But in order to make this a little bit more easy, I already have this assembled and loaded into RAM. Now, let me showcase the paper computer in itself. So on this side, we have the working stack. I like to put it vertically, and in this case you can see the offsets are numbered from top to bottom. That means that the stacks will grow from top to bottom as well. It is also common to show the stack in this way from left to right, okay? Because for example, if we have a number like 1337, we are able to read it from left to right as a big endian number. In this case, if we had here 1337, we could also read it from top to bottom as a big endian number, okay? I tried to put it left to right, but it was a little bit difficult finding a layout that fitted all the information I want. Okay. So now here we have the return stack, and these are for the pointers for each individual stack. So even though we can see here, for example, if we push a byte to the working stack, we can see that the stack pointer, okay, the byte at offset 0 is occupied, and then the next byte would be pushed to this offset, so the working stack pointer here would be 1, and when it starts it is in 0. Okay, now this is the program counter, and this one is 2 bytes in size. Okay, and now here we have the only device the paper computer uses is the console device, and even then it only supports 3 of the ports of the console device. One is the vector. We put here an address. For example, let's say we have a routine in this address at address 0180. If our routine starts here, we could put a vector to 0180, and that would tell the let me make this bigger. That would tell the computer that when there is console input, you should run the code at that address to process it. Okay, and this is just the read and write ports. We will see shortly how they work. Then here we have an emulated console, just like the one we use here for Linux. Okay, so it is just a console. Of course, there is no underlying operating system, but we can receive a byte stream, and we can output a byte stream here as well. Okay, so here will be the output of our Hello World program. Here we have a reference, and this little space I just use it to to put a short description of what the program should do. Okay, on the far right we have the instructions that we will read in a moment. And then we have the memory pages. We start with the 0 page. This page is special because you cannot load ROM, you cannot load both to the 0 page. When you start the CPU, well, when you start the computer, it will be zeroed out. So even though here you see blank, imagine that this is full of zeros. So all the memory is zeroed out, including the stacks, the pointers. In this case, I'm going to put it here, is we start with the PC at 0100, which is this address, the first address at program page 1. After program page 1, we have program page 2 and 3. And beyond that, we don't have more memory installed. So it would be an error trying to access this memory. Okay, but honestly, who needs more than 1 KB of RAM? It should be more than enough for everyone. Okay, now let's read quickly the instructions to see how this would work. So first you would get the Occidental source code and assemble it yourself, or copy a ROM to the program page. Don't forget to update the symbol list and comment the empty space. So you can use the back side of the page to make annotations, or you can scribble comments and arrows in the page. It is your computer, so feel free to do whatever you want with it. But also please consider taking care of it so you can use it many times. Now, in this case, the code has already been assembled. Okay, but we would be, the first step, or the 0th step, is already done. This source code has already been assembled and loaded to the program page. Okay, then the program counter the PC begins at address 100 hexadecimal, which is 256. Okay, so if we do echo, then inside double parentheses, we can run an arithmetic expression in bash. Actually, in this case, I'm using the C shell, but it should be the same. So we have, okay, let me just open bash so I don't confuse you. So we have echo, and then 0x0100, and we can see that this is 256. Okay, so when the computer starts, we always start at this address. We cannot start evaluating code out at the 0 page, and we cannot start evaluating the other pages as well. We always start at this one. Then this is called the on reset vector, because every time the computer starts, it points here. This is like the main in a C program, or the entry point. Then the 0 page starts uninitialized, zeroed out, as well as the stacks and their pointers. Now the next instruction is to fetch the byte at address pointed by the PC. Okay, so the first address, we can the first byte is A0. How can we, okay, we already have the byte. Now we can see the first byte is always decoded as an opcode. The remaining bytes in the bytecode may be more opcodes or data like numbers or ASCII characters. So let's open this link here, the opcode reference. And here you can see a table of how each opcode is encoded, but also of how each opcode is laid out in the opcode space. So we have one page of opcodes, and then if we go here, we can see what each opcode does. In future videos, we will be exploring each opcode separately. But for now, we can just do the hello world, and we can dig in later into this information. Okay, so how do we use this? If you can see, it has these indexes at the top that start from 0 to 0f, and also on the left, we also have them from 0 to f0. So the byte we are searching is A0. We go to the A0 here on the left, and then we match it with the 0 on the top, and we can see that A0 is the opcode for lead 2. Okay, so while we do this, we can simplify this as well. Okay, no, maybe next time, because I don't want to confuse you. All we need to know is that this is an instruction that will push 2 bytes to the stack, to the working stack. Which bytes? The 2 following bytes in RAM. So let us color this as one instruction. Let me use, I don't know here. Okay, no, I think it was the same color. Let me use green. This is our first instruction, lead 2 0112. So let's do that. Oh, okay, so here, once we have decoded, first we fetch the byte, then we decode it, then we are going to execute it. So we execute an opcode by evaluating its effect on the stack, their pointers, the RAM, the program counter, and the console device. The symbol lists are short 2-byte big endian constants. The low byte may be referenced independently. Okay, so here it is talking about a symbol list. This is something we don't see anywhere here. So let's make it. Let me see. Okay, let's make it at the end once we have all this bytecode figured out. So next we have this load absolute keep and dupe instruction. The load absolute keep would be this byte 94, and we can go to here to 90, and then we search the column 4. So 94 is load absolute keep. Then the following byte, okay, so let me see. Okay, let us do step by step, so we don't forget to do anything. So first, let's execute this opcode. We just push 0 1 1 2 to the stack, and now the stack pointer is in 0 2. Okay, because this is the next offset that we would push a byte. Then the program counter advances to 0 1 0 3. So we also need to update the program counter, I'm sorry, the program counter. Okay, now it says repeat until you reach a break opcode, which is 00, and if there are no more events from the console input stream, then the program is done. The CPU keeps waiting for more events until you imaginary turn it off. Okay? So what we just did is everything that the CPU does to fetch, decode, and execute an instruction in UXN. And the rest is just practice for us to understand how this works. So now we are at PC 103 hexadecimal. We already saw that this instruction corresponds to load absolute keep. And load absolute keep will load a byte from this absolute address. Now, if you can see here, I also have the same offsets here and here. So how can we locate this address 0112? We go to this column. Here we see we are in 0110. If we add 2, then we would be at this address. This is the address that is searching. Okay, and this corresponds to the letter H, as we have seen before. So now that we know that this stands for the string hello world, this is up until the end. Let's mark this as our string with another color. Let me see. Let's make it blue. Okay, so this blue section here is our string. Then we are going to load the byte at this address, which turns out to be 48. Okay, so here we add, here we push 48. We increment the stack pointer, and then we advance the PC once more. So now we are at 0104. 04. Okay, I am going to mark in red the opcodes that we have already visited. So we have already evaluated this one. Oh, let me actually. Okay, orange, in orange. We have already visited this one, and now we are going to evaluate this one. So first we locate that this is the opcode that is being pointed by the program counter. Now we go to our table and we search for the opcode 6, which is dup. Dup stands for duplicate. So in this case we would duplicate the top of the stack and increment the stack pointer. Okay. Then we are at this address, so we need to increment the PC as well. Now let's decode this byte 20. If we go to the table, we can see that 20 stands for GCI, and we can click here to see what it means. So it is a jump conditional immediate. It pops a byte from the working stack, and if it is not 0, it moves the PC to a relative address at a distance equal to the next short in memory. Okay, otherwise it moves the PC +2. Let's see how that looks. So this 20 would be the question mark in the Occidental syntax. We can also see here in the runes that this is this is the immediate rune for GCI instruction, and GCI stands for jump conditional immediate. So what this opcode would do is it would take the top of the stack, which is currently this byte 48. If it is 0, then it will sorry. If it is 0, then it would fall through to this code here and evaluate this. If it is non-zero, it will jump to this other label here, to the corresponding or matching closing brace, which is an anonymous label. In this case, 48 is non-zero, so we would jump here. Okay? And how many bytes do we need to jump? If you can see, we need to jump 1, 2, 3 bytes, and we would be at this position. And if we check here, let me color all this in green again. So all these are one instruction. This is the opcode, and this is a relative short to where we need to jump. So in this case, it is telling us that we need to jump. Oh, which color was it? Orange. We need to jump 3 bytes ahead. But we don't jump from this one. We need to jump from the last one, which is part of its argument. So it would be 1, 2, 3, and then we jump to this address, which is 010B. So we update the program counter. We have now evaluated this opcode, and we are now at this position here, ready to evaluate this line. Okay. And also when we do that, we consume the top byte, and then we need to go back, make our pointer here go back 1, because we have popped a byte from the stack. Okay. This happens because that is why we need to duplicate it here before we check this conditional, because if we don't do that, then we would have consumed the byte here, and then we would have nothing else to print, as we will see in a moment. Okay, so we jumped this 3, we can see is the pop 2, and break. So even without looking at the table again, we can see that these 3 bytes correspond to these ones. So I am going to color this, and I'm going to use another color for this, so we can remember that this is the code that is right here. Then, for example, text here would be in green, and the rune would be what tells us which instructions it is. So this is text. Then we have load absolute keep dupe has already been evaluated. Okay. Then the 003 is the green part, so let me just put this here in green. And remember, this is a label. Okay, so this is just to remember that after this instruction, it also has 2 raw bytes as parameters, just as this instruction here above. Okay. So now we have this syntax, which is a hash, no, a hash sign and 1/8. If we go to here, we can see that the hash stands for literal number. Okay, and if we go now to the table, we can see that it has here 80. So 80, we can see it stands for lit. Okay, lit is very similar to lit2. It just pushes 1 byte instead of 2. Okay, so it's easier. In this case, it is pushing the byte 1/8. So again, this is one instruction. This is one instruction, and this is the opcode, and this is the parameter that we are going to push. So now we are going to evaluate it. We are going to push 1/8, increment the pointer. Then we are going to advance the PC to 0D. Okay, so the PC is not always incremented once. It can be incremented once, twice, or an arbitrary number if we jump to any other place here in the RAM. Okay, so now we have 4818 in the stack. And what is this? Does this 18 mean? It means the console write port. Okay, so we are going to now mark this as green, and we have evaluated this one, so this is in orange. We are going to now evaluate this opcode, which stands for device output. So we are telling it to the device output, to the device port 818, which is the console write port. You need to send this byte 48, which corresponds to the first letter in our string. Okay, so let me color this in blue. I think it was this one. Okay, so now this is the string that we have here. And as we saw when we were doing it here in this REPL, the first time that we evaluate this expression, it will print H to the console output. Okay, so now again, we can go back to the table and see that 17 corresponds to DO. Let me go here, here, here. Yeah, this one. So we go to 10 and then 07 is DO here. Okay. And what DO does is it will print the letter H, capital H, to console output and consume these 2 bytes from the stack. So we now need to update the stack pointer, and let's mark it as evaluated. We advance the program counter 1 to 0E, 010E. Okay, so now we have evaluated this one. Now we are going to evaluate the inc2 instruction. which is 2, 1 in hexadecimal. Okay, we go here to the left column, we have 2, 0, and then 0, 1. It is the opcode inc2. So what does inc2 does? It will increment the top short, and remember, a short is just 2 bytes being treated as one number. Okay, so this is the short that it will increment, and we are going to do this. The stack pointer doesn't change because we didn't push nor pop any more items. We just incremented this in place. Okay, now that once that we have incremented that, let me mark this as evaluated. And you can see that this program is very simple and we are almost done. We only have to run one more instruction, and then this instruction is the one that will actually make us jump to this label here, and we will repeat the code until we reach this how is it called, like this edge case, in which we will terminate the program. Okay, so now that we know the addresses, let's see at another thing that the assembler does for us. Let's put a symbol list here. So right now, by convention, the first this address here of program page is called at on reset, which is the reset vector. Then we have the while. While starts before load absolute keep, so we know that while is this address. Okay, it's 3 bytes past this instruction here. So at address 0103, we would have the label while, and at address 0112, we would have the label of the start of our text. Okay, so this is something that the assemblers also do for us, to keep track of the numbers and the addresses that it will replace in the bytecode, because by the time the CPU sees your code, there is no textual labels or variables of any kind. For example, here 0112, once the assembler had this mapping that this label corresponds to this address, then it just replaces the label that we are using here for the absolute address, like this. Okay, that's all it does. So now let's check this last instruction, 40. If we go here, we can see that 40 is GMI instruction. GMI stands for jump immediate, and the syntax is the exclamation mark that we can see here. Okay, so we are going to evaluate this, and I will put this in green, so just we remember that this would correspond to the parameters that we have here. So these raw bytes are the parameters for this opcode. this one. And this is the opcode itself. So now let me mark this as orange because we are going to evaluate it. And all we need to do is see, here is the address. Remember, this is a relative offset. I found the best way to calculate these offsets manually is to do it, to just subtract 10,000 hexadecimal to the hexadecimal number you want. So in this example is FF, F1. And you can easily do this subtraction by hand without needing to convert to decimal. And we can see that it is minus 15. Okay? So it is telling us that we need to jump 15 bytes back to where the at while label is. Okay, and now let me just mark these labels in, I don't know, in orange, in yellow. No, yellow is too, maybe this one. Yeah, so a dark yellow. And the rest here are just comments. Okay, so now that we know we need to jump back 15 bytes, we need to start counting from the, again, from the end of the parameter, not from where the instruction starts. So from here we go 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, in this case it would be from here to here then. So here it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. When we go back 15 bytes, we are back again at the load absolute keep instruction. Okay. However, notice that now the pointer of the string has incremented. Now it doesn't point to this byte anymore, but to this one, to the next character in our string. Okay, so now I'm not going to explain all the steps again one by one, but I will still do them manually so we can see how the program would continue. Okay, so we have the load absolute, which is 9.4. So we load this byte 6.5 here. Oh, by the way, I forgot, when we jump here, we need to set the program counter back to 0103. Okay, so now we are here, and this time around, let's mark this in yellow. So now we are going to evaluate again this one. And notice how we are not going to reach this code again ever, because this is not part of the loop. So this is just to prepare the pointer of the string for the loop. So now we load 6.5. If we go back to the ASCII table, we can see that 6. If you look at this column here, this is in decimal, so it is not A. You need to look in this middle one. 6.5 is the lowercase e. Okay, so that would correspond to the e in hello. Okay, and after that we check again. Okay, so this increments because we pushed a byte. and we also advance the pointer 1 byte. Now we are again here at dup, so we need to duplicate the byte here, increment the pointer, and I'm going to start to doing a little bit faster. Okay, now we have this duplicated. We need to check if it is non-zero. We need to jump 3 bytes. Since it is not 0, we pop this from the stack and we jump to 010b. And again, I forgot to update the pointer when I did the dub. But let's try not to forget doing that. I just don't want to spend too much time making this repetitive for you. But you feel free to do it by hand and take your time. Okay, so now we have jumped here. Now we need to push again the port, the console write port 04, and we increment yes, to D here. Now 17 is DEO, so now we are going to send to the console write port, and we can also put it here. We are sending the byte 65, and when we do that, we consume these two, and we output here the E. Okay. So, oh no, it would be E. I'm sorry. It is. I have been suggested that we could make a like automated version of this in the same spreadsheet. And while I think it is nice, I also think that doing it by hand is actually easier than doing it as I'm doing it right now on the spreadsheet, because on the paper you can easily erase or make changes that takes way too many clicks and mouse movements in my case. But I don't have a camera to show you. Well, I don't have a setup to use with with pen and paper, but I will try later if I can do that. Maybe it is even better for explaining. But anyway, we are at Dio. We are at this address. This 21 corresponds to the int2. So we are going to increment the pointer, and we are going to advance the program counter. We evaluated this, and now we are going to do the jump back to load absolute keep again. Okay, so we evaluate this, we jump here, so we need to update the program counter, and we are back at load absolute keep. Now at this point I will not make any more comments. I will just try to concentrate to do this without any mistakes, and just feel free to follow along. Either if you printed the computer, just you can do it by hand, or just follow me on the screen. Okay, so now the pointer is pointing to this address 0114. So we push 6C and we advance 1. Okay. Now we are here. We duplicate it. We know that 6C stands for the L. So Now that we have duplicated, we need to move to this one. This one checks if it is null. This one is not null, so it will jump 3 bytes. We have jumped 3 bytes here. Oh no, but from this point to this point, so it is B. Now we are going to push 1/8 again. 04. I forgot to update here. And we need to update the program counter to ED. Okay. I mean, not ED, 0D. It is too small here. Okay, so we have pushed. We are 4. We move the PC. Now we are going to print the character to the console write. So in the console write port now it would be this, but a side effect is that we also print the letter L here. While we consume these two and advance to the next address, which is increment 2. Okay, so now we will increment this. We move the PC again. We have evaluated this. And now we jump back again. Okay. We jump back to 0103. But now the pointer we have here is pointing to this byte, which happens to be another L. So at this point, we are going to fast forward to the exclamation mark. Okay, here. So now let's say we have already printed all this. The space would just leave this blank. Okay. So now let's say we are at PC 0103, but now we are at this, we have the pointer to 010D. Okay. So we have already printed all the characters up to the last one. Then let's just do the last 2 iterations so we can finish this explanation. Okay, so we are at this address. We load the absolute value for 21 hexadecimal is where it is here. 21 hexadecimal is the exclamation mark. Okay. So we load the byte. I'm not going to update the PC and the working stack pointer, so we can just see this a little bit faster. But basically, we load the 21 here, then we duplicate it, then we check if it is 0. Since it is not 0, we pop it, and we jump here. which is when we push the port and then we output the port consuming these 2 bytes. So at this point we have already printed the exclamation mark. Then we increment one last time the string pointer. Now it is pointing to the null terminator. Okay, we jump back to load absolute keep. So now we load 0. Then we let me just mark this again in yellow. Now we are going to duplicate it. Now we are going to do our comparison one last time. This time, since it is 0, it will not jump the 3 bytes after to continue printing. Instead, it will fall through to our ending code, which will just clean the 3 bytes that we have still remaining. Okay, so we are going to do the comparison. It is 0, so now we are going to do 0, 2, which is pop. We can see here 0, 2 is pop. So we are going to pop the null byte. And then let me just update here. We are in 0108. Okay. Then we evaluated this. So let me mark this as evaluated. Then we are going to evaluate opcode 22 in hexadecimal is pop 2. Okay, so we are going to pop the remaining 2 ones from the stack and advance to this one here. Okay, so now what does the instructions here say? Repeat until you reach a break opcode, and if there are no more events from the console input stream, then the program is done. The CPU keeps waiting for more events until you imaginary turn it off. Okay, so in this case, when we reach the break, we will halt in the sense that the machine will stop doing work, but it is not off. So for example, even if we have reached this break, if later on we receive console input and we have a code to handle this event, then the CPU would wake up and evaluate the code that that handles this event, because UXN is event based. Okay, so even though we only have one device is all we need to understand how this event based nature works. So now let's evaluate this one. Let me mark this as yellow. We are in break. Even though we break, we still increment the PC. So the PC would go here to 0B, 010B. Then the computer completely waits. We have cleared the stacks, so there is no leftover garbage on the stack. We have printed hello world, and we have finished our program. Okay, so that's it for this example. Let me see how much time we have spent here. Okay, I think we have time for the other one, because this one is pretty small. Okay, no, I will actually make another video for this one. If you would like to give me input or feedback on the video, the paper computer, the tutorial approach or anything, I would be very grateful. I'm always open to positive feedback. You can either leave a comment or find me on IRC in Libera chat on the UXN channel. Okay, or you can also send me a message at Mastodon. My handle is pop to keep R. So you can reach me here if you would like, and I can also answer you. Or you can go to Libera chat. You can go to the web chat. You can use a guest, or if you have already a nick, you can use that. And then here you can search for UXN. It is not here. Okay, that's weird. But alternatively, you can go to. Oh, I'm sorry. I forget how to pronounce this. Awesome. Oh, awesome UXN. It is on GitHub. And in the very bottom, you can see here a link that says UXN on irclibera.net. And this will actually auto join you to the UXN channel. Oh, so let's say we are guest 1337. Connect. And you can find me here under the user pop to keep R. Let me see. This one. So I am pop to keep, or you can also send me like a direct chat if you don't want to send one to the UXN channel. Okay. I will really greatly appreciate any feedback. This should be adequate to use with children of all ages to learn and teach computing and the basics of computer science, as well as for more advanced users that just want to dispel any kind of mysticism or magic that is happening or that the assembler is doing for you. Now you know exactly what the assembler does. There is nothing magical about it. And you also know how the virtual machine fetches, decodes, and executes instructions. I hope you had a good time. Thank you for watching, and see you around.